Uh, Hello, welcome to another practice problem. Today we're doing problem 5.29 out of the textbook. Here it says the concrete pier shown has a modulus elasticity E equals 29 gigapascals. It is reinforced by 4 steel rods with a modulus of elasticity of 200 gigapascals. If the pier is subject to an axial force of 670 kilonewtons, determine the required diameter D of each rod so that 20% of the total load is carried by the steel. So the first thing, that I think I want to do is probably just, there's a lot going on here, right? So let's just look at a few of the givens that we have. The concrete, we'll just say modulus of elasticity for concrete is going to equal 29 gigapascals. Modulus of elasticity for the steel is 200 gigapascals. Find, let's see, the diameter D such that we want 20% of the load, 20% of 670, right, is carried by the steel rod. Let's draw a free body diagram really quick. If we have just like a split, if we're looking at the very top section here, I just kind of cut this pier. We have 670 kilonewtons. 670 kilonewtons going down. Well, about 20%, we're going to have a force of that, coming down due to the concrete, right? The load that's acting on the concrete coming down, and then the load acting down due to the steel rods, right, which is 20% of it. So, doing this right here, this little free body diagram, just right here, we can actually sum the forces in the y direction equals 0. And then say negative F sub C minus F sub S minus 670 kilonewtons equals 0. And then we could say just F sub C plus F sub S equals negative 670 kilonewtons. I am going to call this equation 1. Okay? So, okay, now what? That doesn't really give us a whole lot of information. We could plug some numbers in with like the loadings, but we would essentially get, adding those together, 670 equals 670. Whoop-de-doo, who cares, right? So the trick here is not the trick essentially, but what we need to do is realize that when we have this concrete pillar right here, right? So if I'm having this load that's applied at this point, this pillar, as this whole chapter is about, is going to deflect, right? So it's going to deflect a certain distance, delta, right? Or I guess you could write it delta L. So what we need to realize is as it's deflecting, that whole pier is deflecting, the concrete is moving, right? A distance of delta, but the steel rods are also moving a distance of delta. So we could write the change of length of the concrete is then going to equal change of length of the steel. So delta, there's a couple of different forms of delta, or the delta L that we have. So what we can say in this one, what we want to use is delta is going to be our force multiplied to the length, we'll say concrete, over the area of concrete multiplied to the modulus of elasticity of the concrete. And then the same thing for the steel. So force of the steel, length of the steel, area of the steel, modulus of elasticity of the steel. So this I will call equation 2. So now, as we have from our algebra skills, we can look at this and say, okay, well now we have 2 equations and almost 2 unknowns. There's 3 unknowns, but we can do some manipulation, right? So, or 4 unknowns actually in this case. But what we'll do is we'll just go ahead and solve equation 2 and solve it for F sub C. I don't know, it's on the left. Make it consistent. So F sub C, right? I'm just taking all the other variables and multiplying them to the other side. So it'll be f sub s L sub s divided by a sub s E sub s multiplied to area sub c, modulus elasticity, and then length. Okay. So now we did some manipulation. I can go ahead and take this portion of it, right, because this portion is f sub c, and then plug it in right here, right? So now I've got f sub s, L sub s, a sub s, E sub s multiplied to a sub c, E sub c, L sub c plus f sub s equals negative 670 kilonewtons. Again, more algebra manipulation. My f sub s, we have one here, and then we have one here. So we're just going to factor them out. So f sub s multiplied to, and then I'm going to rearrange the variables in here. I'm going to put like L over L, A over A, and E over E. So L sub s over L sub c, A sub c, A sub s, E sub c, E sub s, plus 1 equals negative 670 kilonewtons. So here we need to do some rational thinking, right? So what did I just say when we were up here talking about our pillar, right? So when I was talking about this section right here, what was happening? Our deflections are the same, right? That's the whole reason why we were able to do this, right? So if our deflections are the same, both the starting point and the ending points are the same, which means our L's are the same, which means they go to 1. So we can rewrite this as f sub s, a sub c, E sub c divided by a sub s, E sub s plus 1 equals negative 670 kilonewtons. Okay, so now we're almost to a part where we can start throwing in some values here. So we got one more relation. I mean, this is a constant right here. 670 is a constant. 1 is a constant. We know because the modulus of elasticity, both the concrete and the steel are given, and then the force right here of steel, we know is going to be 20% of 670. So those are all knowns. What are we actually looking for, right? So if we go back to our problem statement, it says, find the diameter of each rod so that 20% of the total load is carried by the steel. So we're looking for diameter, right? Which means we want the area, but we want the area of the steel. So in this case, we're looking for A sub S, right? But what we can do is make a relation of A sub C in terms of A sub S. So then we would only have one equation with one unknown. So how do we do that? Well, if we look at our figure here, they were nice to us and they give us a square, right? So this is 250 millimeters by 250 millimeters, right? And that's the area of the total piece, right? So if we take the total piece and subtract these pieces here of the steel, right, that'll give us the concrete. So we can say the area of the concrete is then going to equal the total area, which is going to be 250 millimeters squared, right, because that's the area of the square, minus the area of the steel. Okay? So this relation right here, that's what we can use to go ahead and plug into this equation right here. So I'll rewrite this again. We'll use a different color so we're doing something new. And we will say f sub s multiplied to, on the right, 250 millimeters squared, right, minus a sub s multiplied to the modulus of elasticity of concrete. Notice I put two parentheses here. There's a parenthesis there and a parenthesis there. So this 250 millimeters squared minus the area of the steel, this whole thing has to be multiplied to the modulus of elasticity, because between these two pieces up here, it's multiplication, okay? So don't mess that up. You can't just like square the 250 and then multiply e to each. Well, I guess you could do it to each piece, but just do Don't be careful here with your algebra. Again, we have a sub s, e sub s, and then plus 1 multiplier equals negative 670 kilonewtons. So now it's a nice, easy little equation here. Not exactly easy, but you can do your algebraic manipulations here. The modulus of elasticities are both in gigapascals, right? So that's gigapascal divided by gigapascal, so the units cancel there. This force here is going to be in kilonewtons, and this force here is kilonewtons. So kilonewtons right here and here, this divided by that, those units go away. So the only units you would have left are millimeters squared, which is exactly the units for an area. And if you do this correctly, which I'm not going to do because it's algebra and this isn't an algebra class, your area should be, I already have it written down, 2,186.369 millimeters squared. Okay? But if you remember, this is the total area of the steel. So let me go back up to that figure, right? So that's the total area of the steel, right? Because the area of the concrete minus the area of the steel. But we have 4 steel rods, right? So 4 steel rods. What does that mean? We have to go back to our value here and say, well, this is going to be our area of 1 steel rod, so this is going to equal this 2,186.369 millimeters squared divided by 4. And you should get A sub s equals 546.59225 millimeters squared. So we're almost there, right? So the next thing we can do is just remember what's the formula for area, and we're looking for diameter. You could use, you know, pi r squared, but because we're looking for diameter, it might just be easier to use pi over 4 diameter squared, right? And that's what I'll use. So pi over 4 diameter squared equals 546.59225 millimeters squared. And then solving for diameter, you get 26.4 millimeters. And then you get a big box and a check mark and a happy face, because that's the right answer. Thanks.